Hey there. For as long as we've been human, we've looked up at the night sky and wondered, how do you make sense of it all? How do you take that beautiful, overwhelming chaos and turn it into something like a map? A map you can actually read. It's a question that's really at the heart of all astronomy.
I mean, we've all been there, right? You're outside on a clear night, you look up, and there are just thousands and thousands of tiny lights scattered across this huge, dark canvas. It's absolutely stunning, but where do you even start? How do you begin to get your bearings?
Well, that's what we're going to talk about today, because turning that chaos into order, into a map of the universe, is exactly what astronomy is all about. And we're going to dive into the absolute fundamentals of how that map works.
To build this map of the stars, we're going to start with a tool you've literally had with you your entire life, your own body. Because really, before you can map anything, you've got to figure out how to measure it.
See, here on Earth, we use miles or kilometers. But in the sky, that doesn't really work. We can't just pull out a cosmic measuring tape. From our point of view, everything, the moon, the planets, the most distant galaxies, it all looks like it's just painted on the inside of a giant dome. So astronomers had to get clever. They use angles.
And what's so cool is that you have a surprisingly good tool for measuring angles right at the end of your arm. Seriously, go outside tonight, make a fist, and hold it out at arm's length. That fist covers about 10 degrees of the sky. It's a trick as old as stargazing itself, and it really works.
This whole idea is called angular size. It's not about how big something actually is in miles, but how much space it appears to take up from where you're standing. And this is where things get interesting, because a tiny thing up close can look just as big as a gigantic thing that's super far away.
And the most incredible, mind-blowing example of this is the sun and the moon. The sun is enormous. It's 400 times wider than our moon. But in what has to be the most amazing coincidence ever, it's also about 400 times farther away. And the result? From right here on Earth, they look like they're the exact same size in the sky. It's the only reason we get to see a perfect total solar eclipse. Pretty wild, huh?
So, using your hand to measure angles is great. For you, in your backyard. But what about your friend on the other side of the planet? How do we talk about the sky so that we're all on the same page? Well, for that, we need to go from a local view to a universal one.
Now, the simplest way is what's called the horizon system. It's really intuitive, and it's all about describing where something is in your sky right now from where you're standing. All you need are two numbers, altitude and azimuth. Let's break that down. Altitude is just how high up something is. 0 degrees is right on the horizon. 90 degrees is the zenith, the point directly over your head. Easy enough. And azimuth is just the compass direction. We usually say north is 0 degrees. So if I told you to find a star at an altitude of 30 degrees and an azimuth of 90, you just face due east and look about a third of the way up the sky.
Okay, but here's the catch. If I give you those coordinates, they're completely useless to my friend in, say, Argentina. A star that's directly overhead for me might be below the horizon for them. So this local system, it doesn't work for a global map. We need something better.
And the solution to this is one of the most brilliant ideas in astronomy, the celestial sphere. Just imagine that the Earth is inside a gigantic hollow ball, and all the stars are painted on the inside of that ball. Now, it's not a real thing, obviously, but as a model, it's a game changer. It gives everyone everywhere the same frame of reference.
The easiest way to picture it is just to imagine taking Earth's own grid and blowing it up. So Earth's north pole points directly at the north celestial pole. Our equator expands outwards to become the celestial equator. And just like that, we have a fixed grid for the entire sky that doesn't change no matter where you are.
So here's the bottom line. What this gives us is a universal address for every single star. Instead of your personal altitude, we have something called declination, which is just like latitude on Earth. And instead of your personal azimuth, we have right ascension, which is just like longitude. With those two numbers, any astronomer on the planet can find the exact same object.
All right, so we've got a 2D map. We can pinpoint any star on our celestial sphere. But what about that third dimension? What about distance? How in the world do astronomers measure how far away a star actually is? For that, they need a cosmic yardstick.
The most basic way we do this is with a clever trick called parallax, and you can see how it works right now. Just hold your thumb out at arm's length, close your left eye, and look at your thumb. Now switch. Close your right eye and open your left. See how your thumb seems to jump back and forth against the background? That little jump? That's parallax. So astronomers apply this same idea to the stars. As the Earth orbits the Sun, our point of view shifts by about 186 million miles. So they take a picture of a nearby star in, say, December, then they wait 6 months when Earth is on the other side of its orbit and take another picture in June. And just like your thumb, that nearby star will appear to have shifted slightly against the much more distant background stars.
And by measuring that tiny, tiny angle of the shift and using a little bit of high school trigonometry, we can calculate how far away that star is. This method is so important that it gave us a whole new unit for cosmic distance, the parsec. A parsec is simply the distance to a star that has a parallax shift of 1 arcsecond. And an arcsecond is just a tiny sliver of an angle, 1/3600th of a degree. It turns out to be about 3.26 light years.
Okay, let's put this to the test. Here are 4 stars and their measured parallax angles. Think back to the thumb trick. Does your thumb seem to jump more when it's closer to your face or when it's farther away? With that in mind, which of these stars is the closest one to us?
And the answer is Sirius! That's right. Just like your thumb, the closer an object is, the bigger its apparent shift, the larger its parallax angle. Sirius had the biggest angle on that list, and that means it's our neighbor, relatively speaking.
This all boils down to a really simple fundamental rule. It's an inverse relationship. The farther away something is, the smaller its parallax angle is going to be. More distance, smaller angle. It's as simple as that.
Okay, let's step back and see what we've accomplished here. We've gone from just feeling lost in the night sky to actually having the tools to navigate it. We've covered a lot of ground, from our own 2 hands to the unimaginable distances between stars.
So, let's recap what's in your new cosmic toolkit. You now know how to measure the sky using angles. You get the difference between your local horizon system and the universal celestial sphere. You understand the ingenious trick of parallax that lets us measure distance. The night sky is no longer just a random splash of lights. It's a map. And now you know how to read it.
And that right there, that changes everything. It means you can look up and not feel lost, but feel curious. You have the framework to start your own journey of discovery. So the only real question left is, where do you want to go first?